All right, in this video, we're going to talk about 2.6 Objective 10, where we classify discontinuities. This is the discontinuity at x equals -1. This is vertical asymptote here. In the graph, removable. No, it's non-removable because it cannot be made continuous at x equals -1 by redefining f of -1. So that is A. Let's classify any discontinuities in the function below, given x squared minus 8x plus 7 over x minus 1, and we're interested in x equals 1. Let's factor that numerator if we can. So that's x minus 1 times x minus 7 over x minus 1, and x cannot be equal to 1 still. So that is a removable discontinuity. So if we would define, I stick 1 in here, 1 minus 7 is -6. Then I could remove the discontinuity, the hole in the graph there. So that's removable. Let's look now in the numerator. We have x times x squared minus 6x plus 8, x times x minus 7, and that's x times x minus 2 times x minus 4 over x times x minus 7, and that will cancel, giving me x minus 2 times x minus 4 over x minus 7. X still can't be 0. There's a removable discontinuity at x equals 0. And there's a non-removable and infinite discontinuity, a vertical asymptote at x equals 7. Okay, so now we have two different functions that look very similar, but they're going to be different. We have f of x is equal to x sine of 1 over x, and g of x is equal to sine of 1 over x. So does the function f of x is equal to x sine of 1 over x have a removable discontinuity at x equals 0? Yes, it does. So this function sine of 1 over x, it has a vertical asymptote. The 1 over x part has a vertical asymptote at 1 at 0, because 1 over 0 is not defined. However, sine function takes on values that are between -1 and 1. I can't really tell you what sine of infinity or sine of negative infinity is. It just keeps repeating between -1 and 1, but that doesn't matter, as I'm multiplying that constant, whatever it is, between -1 and 1 times this number here that's 0. And so this is not 0 times infinity, really. This is 0 times something between -1 and 1. That's going to go towards 0. So although it's not defined because of this 1 over x at 0, we know it's getting closer and closer to 0 because of this 0 multiplier that's here. So that's A. It has a removable discontinuity because the limit of f of x is x sine of f of x equals x sine of 1 over x as x approaches 0 is 0. And you can prove that with a table. We could do that with some other limit properties and methods. You could analyze the graph to show you that. But what's going to be different here is if I remove that multiplier of x, then I don't know what sine of 1 over x is doing. It's oscillating between -1 and 1. It really doesn't have a limit. It's also just not defined at 0 because of 1 over x not being defined at 0. So it doesn't have a limit. as x approaches 0. So no, that's not a removable discontinuity there. Check the graphs out, see what those look like, and how they're different. But it's going to be important to pay attention to things that just because you see this discontinuity on the inside of the sine function, when you divide by 0, that doesn't mean that the whole function is necessarily going to have that same type of discontinuity, because the things on the outside of the function may help make that discontinuity removable. We'll also have some special trig limits that you should know, and I'll write them down here in case we haven't talked about them yet. The limit as x approaches 0 of sine x over x is going to be equal to 1, and the limit as x goes to 0 of x over sine x is also 1. The limit as x goes to 0, 1 minus cosine x over x is 0, and the limit as x goes to 0 of cosine x minus 1 over x is 0. Those are some special limits where you would normally get 0 over 0 if you just did direct substitution, and you can't get rid of the discontinuity by factoring. So you have to memorize these special trig limits. Really, that's some of what's going on behind the scenes here with problem number 4. But I don't really want to get into that problem, because there would be some algebraic manipulation that we would need to do. So let's just suffice it to say here that you need to memorize these 4 limits, be able to rewrite things as tangent that are tangent in terms of sine and cosine, and be able to make these limits show up, as well as other trig functions that you can write them as reciprocals or quotients or things like that, and make these special trig limits show up when you need to use them. All right, that's it for this video. We'll come back next time and we'll start talking about the limit process for finding something called the derivative. That's really one of our biggest topics in calculus, is to talk about derivatives, which are slope generating functions, and how we look at the idea of the average rate of change, which you had from pre-calculus, and how we're going to use the limit function to help us find an instantaneous rate of change, or the slope of the function at a point. That's really the big idea that's going on in the next chapter, to also finish up with the idea of what the antiderivative is. If I had a slope function, what functions could possibly have been the original functions that would generate that slope? All those topics and more are coming in the next chapter too. So see you for the next video.